Hi, my name is Nanut Panpreuk. I'm a senior in mechanical engineering. This summer, I have a chance to work in a nanoscience computational multi-scale computational nanoscience lab with Kong Chang Che, a PhD candidate, under the supervision of Professor Angela Violi. The project that I am working on is determining mutual diffusion coefficient of aromatic in nitrogen using molecular dynamics simulation. Specifically, I study the effect of molecular structures on diffusivity. And this is the outline of what I will be talking about the topic. I will start with some introduction about diffusivity, then the motivation of and the objective of the project, follow with the methodology used and the results of the study. Then I will be finishing with the conclusion and discussion. First of all, I would like to give a general idea about mass diffusion coefficient, or diffusivity. Diffusivity is a proportionality constant between mass flux and the gradient in the concentration of the species. Or we could put in a simple equation as mass flux equals diffusion coefficient multiplied by the concentration gradient. Thus, the higher the diffusivity, mean the faster the particles diffuse into each other. What we are looking for in this study is the mutual diffusion coefficient, which is a diffusivity for a given pair of species in the system. You might be wondering why the mass diffusion coefficient is important. The diffusivity has an important role in combustion process in predicting the combustion performance. The diffusivity is required in solving the conservation equations of combustion systems, and it is also one of the transport properties that we use in designing chemical or mechanical systems with a higher efficiency. Even though the diffusivity is an important piece of data in combustion, it is an area that has less available data than other transport properties. There is no available experimental data of large molecules at high temperature regions, since the fast decomposition of the molecules at high temperature makes it difficult to measure the diffusivities with high accuracy. In addition, the analytical approach we have been using to calculate the diffusivities is not accurate for complex polyatomic molecules, for the reason I will talk about later. These are the reasons that make the diffusivity an important research topic. The objective of this study is to determine the mutual diffusion coefficients of aromatic in nitrogen mixture using molecular dynamic simulation. There are three aromatic species that I study. The first one is benzene, the second one is naphthalene, and the anthracene. These are the main components in fuel. The pictures show the different number of rings in each species. Thus, from the study, we can assess the effects of molecule structure on diffusivity at high temperature regions. And in this study, I will study the temperature from 500, 700, 800, and 1000 Kelvin. The methodology that I use in the study starts with the target system, which consists of mixture of 3,000 nitrogen molecules and 300 aromatic molecules. And then I run the molecular dynamic simulation of the system at the different temperatures for about 14 nanoseconds, and then extract the velocity of each molecule using software GROMAC 4.0.2 package. After I got out the velocity of each molecule, I calculate the autocorrelation of each species using MATLAB 2007A program, and then determine the mutual diffusivity using Green-Kubo formula. After I got the diffusivity result, I compare the result with analytical method which this one we call it Chapman-Enskog equation. Let me take some minutes talk about the Green-Kubo formula. Green-Kubo formula is the theoretical basis of use of properties. That is a basic theory in use of MD simulation to compute macroscopic transport properties. From the formula, we can see that we can compute the mutual correlation, which is D12 here, from thermodynamic factor, autocorrelation, cross-correlation, and mole fraction. But the main assumption for the gaseous system that I study is that thermodynamic factor is very close to 1 and the cross-correlation is very close to 0. Thus, we can compute the mutual coefficient from the autocorrelation, which we will get from molecular dynamic simulation, and the mole fraction, which is close to the concentration of each molecule in the mixture. Let me introduce you a little bit about the Chapman-Enskog equation for binary mixture. This equation is an analytical method that scientists have been using to calculate the diffusivity. The equation is based on the state principles of the species, which are critical pressure, critical temperature, boiling temperature, and eccentric factor. As I mentioned earlier, that this method is not accurate for more complex molecular structure. The main reason is that the equation is based on the spherical potential average over orientations, whereas the molecular dynamic simulation based on the fully atomistic potential parameter. Thus, there is a reason to believe that molecular dynamic method will give us more reliable results than the analytical method. And Kung-Chang Che and Angela Violi from Violi Lab has a study which compare the molecular dynamic results with experiment result for acetylene in nitrogen mixture. From the chart, you can see that the result from molecular dynamic and the experimental result are less than 4% difference. Thus, this is a reasonable evidence to believe that MD simulation method would give us a reliable result. And these are the results from my study. The first chart that you see here is the diffusivity of different species calculated by molecular dynamic. From the chart, you can see that at the same temperature, the smaller the molecule, the higher the diffusivity. And between in the same species, the higher the temperature, the higher the diffusivity. The next chart shows a comparison of the result of molecular dynamic and CE method, which is an analytical method. For benzene, you can see that the results are very close together. But for the bigger molecule, the result will start have a derivation. Even for a bigger molecule, the difference will be, you can see the difference more obvious. And and I also calculate the deviation in percentage, compare each molecule from smaller to the biggest one. You can see that the biggest molecule has the highest percentage of deviation between MD and CE method. And the conclusion and discussion for this study is the larger molecules have more mass, thus it has the lower diffusivity. And at the higher temperature, the molecules have higher kinetic energy, thus the higher diffusivity. And MD and CE method agree for a smaller molecule, but for larger molecules, CE method does not agree with MD because CE method is based on the assumption of spherical molecules. And finally, the MD can consider the molecular structure successfully. I would like to thank you, Professor Angela Violi and Kung Chang Che, the PhD candidate, in helping me with this project. And also, I would like to thank you, Violi group member in multi-scale computational nanoscience laboratory, for this wonderful experience. Thank you very much.